Welcome to The Explainer. Today, we are breaking down the incredibly complex biology of genetic ALS, and honestly, we're going to look at the unbelievable human-driven momentum that is pushing us closer to a cure. I'm super thrilled to share this explainer with you because the science we're unpacking here, it's not just some theoretical textbook stuff. It's actively changing lives right now. We are literally talking about rewriting cellular instructions, and the stakes could not be higher. Let's get right into it. Okay, so here is our roadmap for today. First, we'll hit the TDP43 biology glitch, then how gene silencing works. After that, we'll look at patients driving observational research, and finally, Target ALS accelerating discovery. We're basically going to zoom all the way in on the microscopic cellular level and then pull way back to the massive global ecosystem fighting this disease. All right, section 1, the micro, the TDP43 biology glitch. We really have to start deep inside the cell to truly understand the root of the problem here. Think of your DNA like a massive library of instruction manuals. Now, the TARDBP gene acts like a highly specific, vital sentence in one of those manuals, and it spells out a recipe for your motor neurons to produce something called TDP43. This is a protein that is absolutely crucial for the health and long-term survival of your nerve cells. Like, it's not optional, it is essential. But sometimes there's a genetic spelling mistake, and that one tiny typo inside the TARDBP gene can have these huge, devastating, cascading consequences for the entire nervous system. To make sense of this, let's just quickly break down the central dogma of biology into bite-sized phases. First, you have your DNA. That's your master recipe locked safely away. That recipe gets transcribed into messenger RNA, which is essentially the courier taking those vital instructions out to the rest of the cell. And finally, that messenger is translated into the protein, the actual worker getting things done on the biological factory floor. In our case today, that vital worker is TDP43. Now, what happens when things go sideways? There's a really clear contrast between a healthy worker doing its job and a mutant protein creating a toxic mess. Normally, healthy TDP43 hangs out right in the nucleus of the cell, the control center, safely doing its job. It's super highly organized. But when that gene has a mutation, the resulting protein gets totally confused. It mislocalizes. It wanders completely out of the nucleus and into the cell's cytoplasm, where it starts forming these sticky, toxic clumps. It's a devastating double whammy for the cell. The nucleus loses the essential worker it desperately needs, and the cytoplasm just gets filled up with toxic trash that the cell can't clear out. Moving on to section 2, the intervention, how gene silencing works. Let's see how modern biotechnology actually steps in to fix the cellular glitch. You might be thinking, well, just get rid of the TDP43 entirely. But we quickly run into a serious biological wall there. Because healthy TDP43 is so deeply essential to survival, we absolutely cannot just wipe it all out. Actually, if we lowered all of it, we'd probably make the neurological situation way, way worse. So the solution demands like sniper-level precision. We need a way to tell the cell to only stop making the bad, mutated copy, while leaving the healthy copy completely alone to do its job. Enter the allele-specific ASO. Through groundbreaking programs like Silence ALS, scientists are using antisense oligonucleotides, or ASOs for short, as highly precise, targeted stop signs. These ASOs are brilliantly designed to bind directly and exclusively to the mutated messenger RNA we just talked about. It literally tags that faulty RNA with a biochemical stop sign, which signals the cell's internal machinery to destroy it before it can ever become that toxic clump. And the absolute beauty of this? It leaves the healthy messenger RNA completely untouched. It's precision medicine at its finest, shutting down the disease at the source. Okay, section 3, the human element, patients driving observational research. Because all this brilliant biology means nothing without the heroic people testing it out. I absolutely love this quote from TARDBP variant carrier Bonnie McKay Harris. It shows exactly how patients are active warriors in this fight. After losing her dad to ALS, Bonnie didn't retreat. She actively enrolled in multiple clinical and observational studies. She represents this incredibly resilient community of people who are totally flipping the script, transforming from passive patients into active, absolutely crucial partners in the research ecosystem. And let me tell you, they are doing the hard, physical work on the front lines. Patients are volunteering for rigorous, sometimes deeply uncomfortable procedures to help scientists map this disease. We're talking extensive annual clinical evaluations, constant blood and urine samples, skin biopsies, and even enduring lumbar punctures to provide spinal fluid. Make no mistake, without patients selflessly providing these biospecimens to discover biomarkers, those precision ASO drugs we just mentioned would literally be stuck in a lab dish forever. Sean McCann, who is living with TARDP ALS, perfectly captures this selfless drive. Patients are grinding it out week after week. Sean's gone through misdiagnoses and painful treatments to get answers, but his main focus? Staying healthy long enough to receive investigational treatments so the data generated from his own body can help protect his niece, his nephew, and future generations. It's profoundly humbling, isn't it? It's a huge reminder of why this research needs to move as fast as humanly possible. Which brings us to Section 4, the ecosystem, Target ALS, accelerating discovery. Let's zoom out to the massive systemic momentum making all this happen. Because the biggest question staring us in the face is, how do we connect that precise microscopic biology to the patients faster than ever before? How do we break down the old silos so discoveries don't just sit around for decades? Well, that's where the Target ALS multiplier effect comes in. They're an innovative organization supercharging the field by intentionally breaking down those barriers. One of the absolute biggest things they do is fund cutting-edge artificial intelligence and machine learning for biomarker discovery, so we can find the subtle fingerprints of ALS much earlier. Plus, they actively democratize science on a global scale. How? By creating crucial foundational tools like CRISPR-corrected stem cell lines or iPSCs and literally giving them to scientists worldwide for free. I mean, that's a real game changer. A researcher anywhere can start testing gene-silencing drugs on human motor neuron models immediately without spending years and millions of dollars making the cells themselves. 30 plus. That's how many peer-reviewed papers were published from the Target ALS ecosystem in just the first quarter of 2026 alone. By aggressively funding AI research and freely sharing those stem cell tools, they've created an explosion of open-source data sharing. It turns isolated, slow breakthroughs into a coordinated, incredibly fast global offensive against the disease. And to put all that momentum into perspective, this is all happening against a record-breaking $315 million backdrop of federal funding dedicated to ALS research this year. Private capital, supportive regulations, deep biological understanding, and a loud, organized patient demand, the stars are aligning in a way we've never really seen before in medical history. So I want to leave you with this final thought to ponder today. As these incredibly precise microscopic tools like gene-silencing ASOs and massive macroscopic networks like Target ALS completely unite with the fearless dedication of the patient community, what incredible breakthrough are we going to see next? We are no longer just treating the symptoms of a devastating disease. We are fundamentally rewriting the cellular machinery to stop it in its tracks. Thank you so much for joining me for this explainer. Keep learning, stay curious, and I'll catch you on the next one.